This PhysCast involves forces on electric charges. Pause the video and read through the question carefully. Let's begin our solution with an interpret step. What is this question really asking us about? And if you read through, you'll see we have two charges at particular locations, and we're trying to find the location for a third charge so that that third charge experiences zero net force. So clearly it's concerned with forces between charges. We'll calculate those forces between charges using Coulomb's law, and because there's more than one force involved here, we'll need to consider the combination of forces, the principle that we refer to as superposition. Let's move on to the develop stage of our solution, where, as we will often do, let's start with a diagram. Here's our x-axis, for example. Here's perhaps the origin of our x-axis, and we're told that at x equals 1 and at x equals 5 we have some charges, so let's draw those in. At x equals 1, let's call that charge Q1, and we're told here that it's negative 3 microcoulombs, and at x equals 5 centimeters we'll have a charge Q2, we'll call it, and we're told that's 6 microcoulombs. Importantly, we're looking for the force on a third charge that we don't know where is going to be located, and we want that force to be 0. So we might like to consider that the magnitude of the force between two charges, given by Coulomb's law, is the Coulomb constant K multiplied by the size of the two charges. In this case we might just call them Q1 and Q2. That would be the force between these two charges, which we're actually not interested in at the moment, divided by the square of the separation between the two. And in this particular problem, for the third charge, we want to find the location where the sum of the forces on that charge equals 0. We're going to combine forces including their directions. So before we go on and do a calculation, it's certainly worthwhile here thinking about what the physical situation is. And we should be able to see there are really three regions that we need to consider here. We could consider the region between the two charges, larger than 1 centimeter but less than 5 centimeters, the region beyond 5 centimeters, and the region less than 1 centimeter. So imagine we put our third charge somewhere in between these two charges here. What can we say about the force from each of those charges? Well, our third charge is minus 2 microcoulombs. So this will feel a repulsive force, a force away from this Q1 negative charge. And it would feel a force towards this positive 6 microcoulomb charge. So remember, like charges repel, unlike charges attract. So if we place that third charge anywhere between these two charges, the two forces will actually be pointing in the same direction. And if they're pointing in the same direction, there's no way that we can add them to give 0. They'll add to give something non-zero. So we can know, without even doing a calculation, that the region where we can put that third charge is definitely not between Q1 and Q2. Let's think about the region here beyond Q2, larger than 5 centimeters. If we think about putting our third charge here somewhere, what can we say about the forces? Well, again, the negative third charge will be repelled by Q1. It will have a force away, and it will have a force of attraction towards Q2. It will have a force towards. So it looks like these two forces could indeed cancel to give 0. But if we think about it carefully, we can see the size of these two forces will depend upon the size of the charge, and inversely with the square of the distance. And so anywhere out here in this region beyond 5 centimeters, I'm always going to be closer to the larger charge. I'll be closer to the 6 microcoulomb charge, and I'll be further away from the smaller charge, the negative 3 microcoulomb charge. So although these forces will be in opposite directions, the force from Q2 will always be larger than the force from Q1. So although they're in opposite directions, they won't be able to sum to 0, which leads us to the region here less than 1 centimeter, where we can again see we will have a force from Q1 that will be away. It'll be a repulsive force, and a force from Q2 that will be towards Q2. It will be an attractive force. But now in this region here, I'm always going to be closer to the smaller charge, and so it's possible for those two to have the same magnitude and opposite directions. So I can consider here that I really do expect, let's say that I call the location of this charge x3, I really expect x3 to be less than 1 centimeter in my solution. So let's move on to the evaluate step in my solution. In the evaluate step, I want the magnitude of force 1, which I can write here as k q1 q3 over r13. That's the separation between charges 1 and 3 squared. I want that to equal the magnitude of the force from charge 2 on my third charge, which I know will be the Coulomb constant k times q2 q3, and then the square of the separation between charges 2 and 3. And importantly here, I've written this as magnitudes, and I want them to be equal because I've already considered the vector nature, the directions, in my develop step here. So importantly here, I'm dealing only with magnitudes. My q1 and q2 will be positive. I've already taken into account the effect of the signs of those. So I'm just going to keep them as positive numbers in here. And I can see in this equation that this expression here must equal the expression on the right hand side. The Coulomb constants will cancel on both sides, and interestingly so will the size of that Q3, that negative 2 microcoulombs, which of course I would call 2 microcoulombs because I'm only concerned with magnitudes, actually cancels on both sides. And we'll come back and talk about that a bit later in the solution. So now I can write down this equation is simply Q1 divided by the square of the separation between Q1 and Q3. And you can see that will be 1 centimeter minus whatever x3 is. So I can write that as 1 minus x3, and that's going to be squared. And that must equal Q2 divided by the square of the separation between Q2 and Q3, and you can see it's going to be 5 minus x3. And I'm writing my distances here in units of centimeters, so whatever solution I get for x3 here will be in centimeters. Now I can rearrange this equation, and there's a good bit of practice for your algebra if you're not quite sure how to do that. It's going to be a quadratic equation. Oops, I forgot to square that. A quadratic equation in x3, and I can write that down. It's going to be the squared term for x3 here will actually be q2 minus q1. The linear term in x3 will be equal to 10 times q1 minus 2 times q2, and the constant term here turns out to be q2 minus 25 q1, and that all will equal 0. And you should have some practice in expanding such algebraic expressions. Now I've left everything here in terms of q1 and q2, but actually it will become easier in my calculation if I put values in here now. So q2 minus q1, remembering I'm only concerned with the magnitudes here, will be 3. So this will be 3 times x3 squared. This combination here turns out to be 18 times x3, and my constant comes out to be negative 69 equaling to 0. And now I want to solve this quadratic equation for x3. If you're not sure how to remember doing that, we can certainly use the quadratic formula. Might be the easiest way here, where I can call the coefficient of the squared term a, the coefficient of the linear term b, and the constant here c, and then I can write down that my solution will be x3 will equal minus b, so that's minus 18, plus or minus the square root of b squared minus 4 times a times c. And when I do 18 squared minus 4 times 3 times negative 69, I get 1152, all divided by 2 times a, which in this case will be 6. And so when I do that calculation, I find two answers. I find minus 8.7 and I find 2.7, and they'll both be in units of centimeters, as I mentioned before. I've got these two answers, but only one of them matches our physical expectation. x3 will be less than 1 centimeter. So this one here looks correct. This one here, we'll come back and talk about that in our assess step. So that doesn't look like a correct solution. So the answer here is we'll place our third charge at negative 8.7 centimeters. So it will actually be out here somewhere, less than 0. Now let's give ourselves a little bit of extra space here to complete our solution with an assessment step. Let's assess to see whether our solution actually makes sense. One quick and easy way to do that in this particular example is I can now straightforwardly calculate the size of the forces from each of these charges on our third charge. So it will simply be the Coulomb constant multiplied by, in this case, 3 microcoulombs, and then the third charge, which we're told is, it's negative 2 microcoulombs, but I'm doing everything here in terms of magnitudes, divided by the separation squared. So if my third charge is at negative 8.7 and this Q1 is at 1, then this is actually going to be a 9.7 centimeter separation, and I'll put that in SI units. And when I do that calculation, I get 5.7 newtons. And then straightforwardly, I can do exactly the same kind of calculation for the second charge. So now, of course, I have 6 microcoulombs for the second charge. Once more, if my third charge is at negative 8.7 centimeters and Q2 is at 5 centimeters, then their separation there will be 12.7 centimeters. I quite conveniently get the same size force. So the magnitudes of those two forces are the same at that location at minus 8.7 centimeters, but of course they're in opposite directions. That tells me quite nicely that my solution does in fact give me the correct answer. What about this 2.7 centimeter solution? If you look back up here at our diagram, this one here is pretty much at 2.7 centimeters, the one in between the two charges, where we said the two forces point in the same direction. And what this solution has done for us is simply found where the magnitudes are equal. So at 2.7 centimeters, the magnitudes of the forces from Q1 and Q2 are equal on our third charge, but they're in the same direction, so they cannot cancel. So it kind of points out it's important to have a physical picture as well as doing the mathematics. And the final point to make here is I mentioned that this solution actually didn't depend upon the value for Q3 at all. One way to think about that is that we've found a position where the force from the two charges gives 0 net force, and another way of thinking about that is that the electric field from those two charges is 0 at that point. So any charge at that location, any charge at a location of 0 electric field will feel 0 electric force.